let's talk about antenna tuning word versus impedance matching, as Don mentioned. So the impedance is at the feed point of your antenna is really determined by where the voltage and current distribution is that happens to exist at that physical point. And it really depends on the physical design of your antenna, how high off the ground it is, and some other physical factors. There are a few antennas that you actually do tune. If you have a stepper antenna that has, motor-driven things that change the length of the elements, then you're tuning your antenna. If you have a magnetic loop, you change the capacitor to resonate the loop to the frequency. I'll admit that in those cases, you are tuning an antenna. Also, we have antennas that have coils that you tap. There are mobile whips that have motor-driven slides on the coil to change the inductance. And those are things that you really do have to admit tune the antenna. But for a normal fixed piece of wire hanging up there, you don't really tune the antenna, as Don was saying. So to understand a lot of what we're going to talk about, the antenna impedance, the feed point, is characterized by having a real value, which is you can think of as being resistive, although it's really a kind of a function, a make-believe resistance, if you will, to some extent, and a reactive component. And we write these out as being the real part, and then the imaginary part, which is the reactive part. If it's a minus J, it's capacitive. If it's plus J, it's inductive. The objective for most of us, most of the time, is we want our transmitter to see 50 plus J0 ohms. That's a 1-to-1 VSWR. Your radio is very happy working into that. That is what most all modern radios are designed to do. So in general, what we want to do is we want to tune out, by canceling it, the reactance, and then take the resistive component of whatever your antenna impedance is and transform that to 50 ohms. So that's kind of the whole notion of what we're trying to do when we match or couple the antenna. So look at a couple of examples of some antennas. If we have a really short antenna in terms of wavelength, say a 40-foot wire on 80 meters, the feed point impedance is going to be ridiculously small resistive component and a very large capacitive reactance. For example, 5 ohms minus J3000. If we were talking about the half-wave end-feds being real popular, being used at field day, the problem with them is they have a very high resistance and reactance, say 2000 minus J3000 or minus J4000 ohms, where it's a half wavelength. But if it's on some of the higher bands, through simulation, I've noticed that they can have like a lower resistive part and a high reactance, like 60 minus J2000. Was a example I got trying to use a 20-meter end-fed on 15 meters. Your dipole in free space ideally has a 72 plus J0. Okay. Uda-Yagi antennas, the big directional beams, they really have a very low impedance typically because of the close coupling between the elements. And most of these antennas actually have an impedance matching network, like a gamma match or a hairpin matching network, actually built into the Yagi antenna, which is part of the antenna when you buy it. Wyndham antennas, the Carolina Wyndham, whatever, if you go up on the wire there, it has a feed point impedance across several different bands of several hundred ohms, 300 to 400 ohms typically. And the reason that they're multi-band antennas is it's got the same impedance on several different bands, so you can transform that down and have basically the same impedance. Historically, okay, let's go back to the spark era up through the 1940s. Hams did not care about VSWR. They never even heard of VSWR. You just adjusted your transmitter for maximum RF current into your antenna. And you had, some networks, capacitors. You could move your coils in and out to change the coupling between them. And that's how guys loaded their transmitters into their antennas up until the 1950s. But once we got coax cable, 50 ohms started becoming commonplace, and we started standardizing on 50 ohm load for antennas, and for the transmitters, that is, or transceivers. And then came the solid state amplifiers, and they were typically broadband. And again, they're designed to operate into 50 ohms and nothing else. So let's talk. We talk about VSWR all the time. VSWR is also can be characterized as reflection coefficients, and even the S11 parameter, the scattering parameter, when you're nano VNA. They all basically are the same thing. They're basically is how far different is that impedance that you're seeing from the 50 ohms. If you have a 1-to-1 VSWR, it means your load is 50 plus J0. That's the ideal load for your transmitter. Say we have a 2-to-1 VSWR. Well, it could be a lot of different values. It could be 50 plus J50 inductive. It could be 100 ohms plus J0. It could be 25 ohms with no reactance. It could be 30 ohms with 20 ohms of inductive or capacitive reactance, for example. These are all examples of a 2-to-1 VSWR in terms of feed point impedance. This got kind of messed up on my editing here at the last minute. One concept that is often used is you characterize VSWR as having a forward and reflected wave, and that the VSWR is a function of the relative amplitude. And that concept is kind of useful for envisioning the standing wave that occurs. That is, you have a peak and a nulls along the transmission line rather than a continuous value of voltage and current. So why does VSWR matter so much today? Well, as we said, today's rigs are designed to operate at 50 ohms. A mismatch generates a standing wave. And what will happen there is you will have high values of voltage and current peaks along your transmission line and at the terminals where your transmitter connects. The high VSWR with the high voltage and current can exceed the ratings of components in the radio. You can basically burn out the transistors, which is, you've seen quite a few rigs even coming in from field for Winterfest that have blown output transistors. The inductors can saturate in your matching networks and overheat. They can change values. Capacitors can arc over and form carbon paths, which are hard to clean up. And your amplifiers can become unstable and oscillate. So particularly with today's solid state radios, it's pretty important that we give them something close to 50 ohms to keep them happy. Solid tubes were much more forgiving than solid state devices. They could undertake some voltage overloads and things momentarily without destroying themselves like transistors do. So let's go back to antenna matching. So there's several different ways and techniques you can use to get the impedance of your antenna down to 50 ohms to make your radio happy. One is to use untuned RF transformers, which are broadband devices. These are quite often, for example, used in most all the end-fed antennas today, although that's end-fed antennas used to use LC networks. Some of them were called end-fed ZEPs at one time. There are balanced and ununs, which is an unbalanced to unbalanced broadband transformer. There are untuned RF auto transformers. which is, a single coil with a tap. The Carolina Windom uses this to match its 350, 400 ohms down to 50 typically. From the old days of old, we have tuned transformers with our linked couple. An example of that would be the Z match, also the Johnson matchbox would be that type of a device. There are transmission line transformers, which is kind of a misnomer here. There's actually transmission line transformers when we talk about balance, but there's also quarter wave sections of a transmission line can be used to match one impedance to a different impedance. Also, transmission line stubs, which are basically a short piece of either open or shorted transmission line added in series or parallel with your transmission line, can actually tune out the reactance for narrowband. And then we have a wide variety of what we typically think of as antenna tuners that sit next to your radio, which are basically capacitors and inductor networks. They can have two or more elements. Typically, the two elements, the L network, there are pi networks, T networks, the SPC, series parallel capacitor, is actually alternate rather than alter-match. And these are all kind of narrowband networks that you have to tune. And depending on the Q of the network, tells you how far you can operate before you have to retune them. So let's talk about broadband real quick. As I said, these are basically will transform a complex load impedance to a higher or lower value. They do not tune out the reactants themselves. And as I said, a very popular use of this is a transformer used for your end-fed. So if I have an end-fed antenna and I try to connect my 50 ohm coax to it, and I measure the VSWR, in theory, it could be up around 60 to 70 to 1, which is not going to work too well. And very few built-in tuners could even deal with any kind of VSWR this high. So let's take Leon's end-fed wires he was using for field day. He has, I think, a 7 to 1 transformer basically tied to the end. So what that does, it takes that, say, 1500 minus J3000 and transforms the impedance down to like 30.6 minus J61 here, which falls within a VSWR circle of 1.5 to 1 or less. And then your little tuner built into your radio can easily adjust that down to get a match. Windom antennas have a feed point 300 or 400 ohms. And as I said, Carolina Windom's use of the auto transformers has set that down to about 50. My 40 meter delta loop has a 200 ohm impedance, so I use a 4-to-1 Ballon. And it matches the 200 to 50 ohms, and it works great on 20 meters. But I have I have no reactance or very low reactance at that feed point. So one of the things I want to make a comment here is, while the antenna matching network could be broadband, the antenna is not necessarily broadband. It can be very not. So trying to use a broadband device may not work too well by itself. For example, if we take the end-fed antenna that's very short, it will have a very low resistance component, literally a couple ohms, very high reactance. And if I put a transformer on that, it will transform the reactance down maybe to a lower value, but it's also going to take that low value of resistance and make that even much more lower. And it actually can make the VSWR worse. So one of the caveats is if the resistance and reactance are significantly different at your feed point, then if you want to use a broadband transformer to transform it down, what you really have to do is tune out the reactance, if you will, and then you can use your broadband transformer to transform the real part of the reactance to your 50 ohms. And so like for the end-fed, you can't use it at all across the whole ham bands necessarily without getting into trouble. I want to make a quick comment about, most of all these transformers are using ferrite or powered iron cores. One thing to be careful of is not to exceed the rated flux density of the core that you're using. There is magnetic flux flowing in the cores. It is not a function of power. It is a function, rather, of the voltage across the core and basically the frequency and the area of the core, which you can see here in the formula I'm showing. The E is the voltage across the core. F is your frequency, N is the number of turns, and AE is the cross section. This other term here is actually a DC term for saturating the core based on the DC current. And of course, that's kind of not relevant for our RF operations here. So when we actually design the core and want to size the core properly, we need to design it for the lowest frequency of operation to ensure the core will not overheat and saturate. The number of turns we use for our transformer should provide a reactance of about 10 times the impedance of the circuit. It's kind of the rule of thumb that's generally used. And why do we want to deal with where we're worried about this? Well, if you have excessive flux density, you can saturate your core. It's going to become hot, which means basically it's burning up power as heat. It can become nonlinear. That can cause your increase in your transmitted intermodulation and distortion. And with ferrite cores, if you oversaturate them, you can actually change the value of the core. And powered iron will recover from saturation, but ferrites will not. So let's give you a few takeaways here real quick. So broadband works well as long as the resistive and reactive parts are close together. If there's big differences, then you really need to tune out the reactance and then use with a narrowband device, and then transform the real part to 50 ohms. And again, you need to be sized, make sure you've got enough iron, if you will, in the core that you don't saturate it for the voltage applied. And since voltage is a function of the impedance, that means that, for example, if I have a transformer or balun designed for 200 to 50 ohms, I can't upscale it and use it like in a daisy chain necessarily to transform 800 to 200, then 200 to 50 ohms and put two back to back of the same design, because that 800 ohms has got a lot more voltage across it than a 200 ohm for a given power level. Okay. So again, it's not, so you got to think in terms of not just power, but how much voltage you're doing. And that's a function of the impedance of the circuit. Okay. So we mentioned quarter wave transmission lines. They have a unique property that if we take they can be used as a narrowband matching device. If you take the square root of your desired input impedance, say 50 ohms, and the actual load impedance, take as a square root of that product of those two values, and if you provide a coax with that impedance, it will actually match. So you have a good example would be like a delta loop antenna fed a quarter wave from the apex, has a feed point impedance around 100 ohms. So if we connect, as I said here, a quarter wavelength of 70 ohm coax, RG59, and we measure the feed point, we'll have 50 ohms, because that quarter wavelength of 70 ohm cable will transform that 100 ohms at the load to 50 ohms at the terminals of the 70 ohm coax. And we connect however much 50 ohm coax we want there, and our system will see a 1-to-1 VSWR. So that is a property of transmission lines that can be used as a very low loss matching device also. But again, it's narrow band. Link coupling. Link coupling's been around forever. it has at least one of the coils is typically tuned to resonance. You look on the internet or anywhere, you'll find the Z-match is a common application of those. The Johnson matchbox, which is kind of legendary matching device, is shown up here on the right. You can see, if I want to bring my cursor here, this capacitor kind of tunes the coils to resonance, and these output capacitors change the loading on the coil. So you pick your kind of ideal, to transform the output impedance, either a higher or lower impedance, back into the high Z here of the coil. And the matchbox has an untuned primary and a tuned secondary. There's other designs that basically have both a tuned, series tuned, if you will, input circuit, and then the parallel tuned output circuit. And underneath there, here's another example that shows basically this. Again, you have a capacitor in series here. So this is series tuned to resonance. This is your output is parallel tuned. And depending on where you connect your wires here, you can get the best match, impedance match into the circuit. And I don't know how this is going to work. Here's one I built decades ago of this type of a matching network. So it's it's got in the middle here is the primary, and then the two secondaries on the ends, and I got some capacitors there. If I can get them up so they can be seen, that tune this thing to resonance, and it does work. And it has a balanced output. I have, in this case here, a pair of banana posts that you can plug the open wire transmission line into. So, and as I said, things like the Johnson matchbox they still go for several $100 at Hamfest. And to me, these are pretty good matching networks. They work almost match anything to anything. So let's talk about narrowband matching again. In general, as I said, you want to tune out the reactance and then transform your resistance to 50 ohms. You can actually get rid of that reactance anywhere in your circuit. You can do it at the antenna terminals. You can do it somewhere along the transmission line that's a convenient place. One way we can do this is with a piece of transmission line that's either opened at one end, which makes it capacitive if it's less than a quarter wavelength, or if it's shorted at one end, then it becomes an inductor in value. So we can actually calculate out the capacitance or inductance and actually cancel the reactance out. And you also can use a bulk capacitor or inductor component as well. But, note this is only going to work perfectly at one frequency. But again, it's a way of tuning out the reactance and then of your circuit. So one of the most common networks around and used quite a bit is the L network. And the L network is basically just two reactances that can transform one impedance to another value. And these are actually pretty commonly found in some of the antenna tuners that you buy. They're found in most of the tuners that are actually inside the radio when you hit the tune button these days. But each circuit can only tune a particular limited range of values. So they're only for a particular configuration that only has a very limited ability to match a circuit. So let's take the case where we have a capacitor and an inductor as our circuit. So basically, the best we can do, this is a Smith chart, which represents, if you will, to the right of the center here are values of resistance that are greater than, say, 50 ohms. And to the left are much less than 50 ohms, right? The bottom here is capacitive. This is inductive. So if my feed point falls, say, here in terms of the resistance and reactive components, which is partially, in this case, inductive reactance, this circuit will work. If I'm down here where it's capacitive, it'll work. But on the other hand, if I have a fairly low value of resistance in a capacitor or inductor up here, this circuit will not work. Instead, I have to go and look at one that has, instead of the capacitor at the output, the capacitor at the input. So what you'll find in your antenna tuners that use this circuit is they have a switch in here. And so this capacitor here can be switched to either the output of the coil or the input of the coil, depending on which way you need to go. I'm also going to note that we've got two different circuits here that can match any particular point. So this one can do, say, here, and this guy can do the same thing here. The issue is that when you do your calculation of the values required for the conductor and the capacitor, you might find them to be one circuit not to be realistic values. That is, for example, if I come up with something that tells me I need 1 microhenries and 2,000 picofarad capacitance, that's probably not going to be a realizable circuit, because just the stray inductance with the capacitor and all is probably going to outweigh the value here. So you have to have, so one of the issues is you have to pick one of the circuit may have a more realistic set of values that you can actually really get a capacitor inductor that are really going to be those values than the other circuit does. So that tends to be an issue with a lot of Q networks, the L networks. The L network, basically the circuit Q, that is the quality, the bandwidth of the circuit, also is a function of the resistance ratio, and you can't control that in your design. It is going to be whatever the input resistance is you're trying to go for versus the output resistance you're trying to match to. And if you have a very high Q circuit, it can be very touchy to tune. And as I said, you can get component values for one circuit or the other, which may not be realistically achievable. Or example, I come a very large inductor and extremely small capacitor, like a 1 picofarad capacitor. I need a 12 microfarad inductor. Well, the 12 microhenry inductor, a 12 microhenry inductor is going to have more distributed capacitance than that capacitor does. So that's not going to work. So you have to, there is an issue with the values. So here's another example of the same thing. And this one just shows for all 8 configurations of an L network, the areas where it can and cannot work. So for example, if I use circuit 1 here, our typical L, I can use it up here and here. I can't use it here or here. So this is just real quick construction. Variable inductors are probably better because then you have continuous variable than tap ones. And again, variable capacitors let you tune better too. But most of a lot of the units that are out there commercially these days, particularly someone with automatic matching networks, basically have step relays that are basically selecting capacitor values and taps on your coil. So they're kind of like discrete value steps. Not you don't have continuously variable values. So anyway, that's kind of a rundown on L networks. As I said, they're very common, but they do have limitations. And somebody came up to me at field day and wanted to know why one radio could work into his antenna and the other one couldn't. And it was all dealing with their the matching networks that he was trying to use with his radios. Pi networks. Okay, so if we get around the Q problem so that we can have our whatever Q value we want, say a value of 10 or 12, for example, without worrying about what's forced upon us by the resistances with the L network. So when I go to a 3-element network, I can control independently my circuit queue. This is the Pi network. This was typically a matching network that was used in most tube transmitters from the 1950s to 1980s. Basically, it will match anything as long as the reactance of this coil, okay, right here, does not exceed the square root of the product of the resistance of the load and the match impedance. So if you have 50 ohms and say 50 ohms, then 50 times 50 takes the square root, So as long as this reactance required here is below that set by R1 and R2, you can match almost anything to anything with a Pi network. And the way you design it, a Pi network, is if we know R1 is 50 ohms, then we know the reactance of C1 value should be 50 divided by the Q, say it's 10, so it should be 5 ohms of reactance. And then based on that, we can calculate the value of C2. And knowing C2, we can then go back and get the value of X for the resistive part. For the reactance that would be tied in here as part of R2, say we basically absorb that into our value of C2 here. So if I have a shunt conductance here, I would reduce the value of C2 to make up for the difference. Or if I have an inductive shunt load here, then I would increase the value of C2, compute it here to equal that of the, to add to it the amount of reactance that was in the load. So this output capacitor basically absorbs the reactance of the load in a Pi network. T network is another 3-element network. They're very commonly used. A lot of your commercial units from MFJ or wherever quite often use T networks, although the cheaper ones use an L network, but the better ones use a T network. And again, the T network has more realizable component values, more practical values than most of the other network designs, which is one reason they do them. And like the Pi network, you start with the figuring out what the Q of your circuit wants to be, and then based on that, you determine the values of your other components in the network. So that's a pretty popular way of matching your antenna. Again, ideally a variable, although some of the units use a tapped coil. And again, your two capacitors. Back in the 1970s, Lou McCoy came up with something called the Ultimate circuit, which is here. It uses a split stator input with a variable inductor here, or tapped inductor core. And then he's got a series output capacitor here. And this was very, very popular back in the 1970s as a matching network. And then some people said, well, instead of this, let's change the configuration kind of around the other way and use what they call the series parallel. So you have a capacitor here, and then you have a resonant circuit here, C2 and L1, and then you have C3 as your coupling output, and C1 is kind of a coupling input. And this is called an SBC tuner. And they were also very, very popular back in the 1980s and 1990s. You don't see them used too much anymore except in homebrew. There's some other variations to talk about. The Drake MN2000, which I happen to have one, actually has a Pi network in it, but it also has a variable capacitor in series with the output. And it actually uses the series capacitor to tune the reactance control on their matching network. And they have a tapped coil, and some fixed capacitors they're put in by a band switch, and then a variable capacitor on the basically in shunt, that is from the hot end of the coil to ground for the output tuning. Dutch ham, PA0FRI, came up with a matching network, but for a single coil that's kind of based on the design that we're talking about for the loop coupling. It's kind of more like a tuned auto transformer, if you will. And that's shown here. You see it has a split-capacitor capacitor across here. Another one tunes this part of the winding, and his output comes off this tap here. So it's kind of like a tuned auto transformer. Although if you want a balanced output, you could always add a secondary winding as well to pull a balanced network off. So let's talk real quick about tuning your matching network. So my recommendation is you need to use an antenna bridge, be an MFJ or Rigmaster, whatever. And instead of tuning up your transmitter and looking at a VSWR meter or the built-in meter on your tuner. And the reason for this is to, first of all, it's really easy to see what's going on with the little MFJs or whatever. You can watch the values as you're tuning it. You minimize interference to other people because you're not really running any power. You also don't, if things are really out of whack, you don't jeopardize the chance that a high VSWR will affect your radio. In terms of actually adjusting the adjustments, if you buy an antenna coupler or matchbox, most of them have units. The recommended settings where you start. In general, what you want to do is minimize the reactance in that whole circuit to minimize the losses. So what you want to do is have the least amount of inductance, L value, in the circuit, and you want to maximize the amount of capacitance that you're using so that has the lowest amount of reactance. But for the L network, you really don't have much of a choice. You have either two choices of L and C values, and that's it. So that's about it. Any questions?
You got a really mismatched antenna, and you've adjusted the impedance so it looks good at the transmitter. What goes out the antenna?
Well, it depends on what kind of transmission line you have. And the losses in the line. So if we have our matching at the transfer, keep it happy, but we have we still can have a very high VSWR on the transmission line. The additional loss from the VSWR is pretty much a function of how lossy your line is. So I'll give you a quick example. I use a Lazy H antenna. It's fed with open wire line down to a balun. Actually, I have a coaxial balun with doesn't even have any iron or ferrite in it. It's actually an air balun. And then I have a very short run of 50 ohm coax into the shaft. So the idea there is there's very, very low loss from that open wire transmission line. So even though I may have a high VSWR on it, I probably don't lose very much power. On the other hand, if one were to take and run some RG58, a long run of RG58 up to your antenna, then you probably would see certainly much more loss due to the high VSWR. But in general, the energy that you think about, people think of reflected energy. The majority of energy that gets reflected at the coupler or at your rig and back up down the line is not absorbed in the coupler. It's reflected back again toward the antenna again, if you think of it in terms of the forward and reflected waves.
You were talking about saturating the core, and if the standing wave, if the ratio is high enough, you're actually reflecting current into the inductor that's saturating the core, right?
No, actually, for most of all your RF devices, the flux density is a function of the applied voltage across the core, not the current. So the B field inside the inductor is for a given size inductor. Okay.
Right. So the problem is if you're trying to transmit too much power, then you'll get the higher voltage to saturate the core.
Right. Well, yeah, obviously higher power will saturate, but also even if you're just running 100 watts. So there's the flux in your core. If you say are running a VSWR through or an impedance ratio, say we're trying to do a 200 ohm to 50, okay, 4-to-1 transform. You've got this higher voltage on that secondary from the 200 ohms with the 100 watts. The problem is with the higher VSWR or higher impedance load is that for the same 100 watts, if I have a higher impedance load, I'm going to have a higher voltage across the core. So if I have a core that's designed to match 50 to 200 ohms, and that does that safely for the 100 watts or kilowatt power level, the problem is that if I try to use that same balun or transformer and instead go to like a 800 ohm load instead of a 200 ohm load, then the voltage is going to go up quite a bit. And when you design these and size out the size of the core that you need to consider the voltage, which is then a function of power and the impedance, basically, right? But it's the voltage across the core that determines the flux density in the core.
Yeah, I got that. Thank you.
Okay.
Lee, thank you so much. There's two topics that I think are endlessly traumatizing in amateur radio. One is what's a balun. The other one is tuning your antenna. So you've ably handled one of those tonight. Next time, I'm sure at some point we'll talk about the vexing mysteries of balance. But Lee, thank you so much for helping us understand the components of antenna tuning. I'm going to go home and tune my antenna so it sounds nice.